Okay, so let's take a look here. I'm going to just quick go over what I did because I'm recording this now. So what did we do? We found the zeros, and we took those zeros and turned them into factors. And then we multiplied the two factors together to get a new trinomial. And that trinomial should divide equally or evenly into the original polynomial, and that's where we're at next. We're going to use long division to divide the trinomial into the polynomial. And then what's left over, we're going to try to solve and find the missing roots. So our goal with long division is to make this first term look like the first term that we're dividing into. So x squared needs to be multiplied by another x squared to turn into an x to the fourth, and those are matched up now. And then we have to multiply all the terms in the trinomial by x squared. So we get negative 2x to the third, and we get negative 8x squared. And then we always said instead of subtracting, we add the opposite. So change each sign to the opposite sign. And then if you do that right, your first terms should always go away. So then what's left over, so we got a negative 6x to the third plus 22x squared plus 28x minus 80. And I like to drop everything down. The reason why is because now it's just like a brand new problem and we start the process all over again. What do I do to the x squared to make it look like negative 6x to the third? Well, I have to times by negative 6x, and it's going to multiply all three pieces. So we'll just distribute. And then you're going to change everything to add the opposite. So this will be positive, negative, negative, and the x to the thirds will add up to 0. And then I have a negative 22 and a negative 12 is positive 10x squared. And then we get I guess I could make that a negative 20x, and the minus 80 drops down. All right, and then the next step, and if everything goes well, this should give us a 0 remainder. So this next step is fairly crucial, is I should multiply everything by a 10, and it should make everything exactly the same as it was. So 10 times x squared, 10 times negative 2x, and 10 times negative 8. There's a good sign. They're identical. And then when we add the opposite, everything reduces out. I'm left with that 0 remainder. All right, so now what do? We take what's left over. By the way, what's left over, this would be considered the slant asymptote. And that's what we learned from last week. So the process for slant asymptote is the same way for finding real solutions or roots. All right, so now what do I have to do? I have to take the remainder, I have to take the remaining polynomial. In this case, it's x squared minus 6x plus 10. And I have to solve that. Well, anytime we're solving, we're trying to figure out where does this have zeros. Now, we know for sure that it's not going to have real solutions. It's going to be imaginary because if they were real, they would be present on our graph. So I'm not even going to bother trying to factor this because I know it's not going to work. We're going to do the quadratic formula. And I like to always put a 1 here just to say A is 1, B is always the number in front of the X, and C is 10. So hopefully you guys are very well versed in the quadratic formula. That's something that you'll use basically throughout your entire math career. Once you learn it, it's always there for you to use. All right, so what do we know? We know, I'm going to just put some blanks and fill them in a second. So what do I know? Well, the opposite of b, if b is -6, then the opposite of -6 is +6. And then we're going to have b squared minus 4 times a times c all over 2a. And since they're imaginary solutions, you might already know what's happening on the inside here. You're going to have 36 minus 40. But 36 minus 40, well, wait a minute, that actually ends up being a -4. And that -4, this red -4 is the discriminant. That's evidence that when I take the square root, I'm going to get an imaginary number. So therefore, I should have 2 imaginary solutions. Now, I like to kind of split this up. If you remember from Algebra 2, the square root of 4 is 2, but the square root of -4 is 2i. So I have 2 possible answers. I've got 6 plus 2i divided by 2. And actually, I'm going to save a step. Instead of dividing the entire thing by 2, I'm going to divide each piece by 2. It's equivalent to divide everything by 2 or divide each piece by 2. And then I'll simplify that. But I also have 6 minus 2i with each piece divided by 2. And then my final answer is just simplifying this. So what do we get? We get 6 divided by 2 is 3. 2 divided by 2 is 1. So my first imaginary solution is 3 plus I. And you might know its conjugate also has to be an answer. So you know 3 minus I is the other solution, and that should show itself here. 6 divided by 2 is 3. 2 divided by 2 is 1. Here are the 2 remaining imaginary solutions. And anytime you have an I, you're going to have its conjugate as a solution as well. So, can you check this off and say, I feel confident in doing this? Because you will most likely have to do a problem very similar to this on the test. Or we'll give you the 2 roots, turn them into factors, divide that, and whatever's left over, then you have to solve. And it could be as simple as factoring, or it could be as complicated as using the quadratic formula. It depends on if the solutions are real or imaginary. Okay. I will be posting these solutions and the video in our classroom. So if you have questions, you can go back and watch it or go back and look at it. All right. I want to talk real quickly about what's going to be on the test here. I don't want you to write this down. I'm not going to give you time to, which is why it's available online. So what have we learned so far? And I know it's kind of hard because we're not face to face and everything's online, and it's fairly difficult to just get a feel for what we've done. So when we started this unit, we called it section 2.0, polynomial review. And this, to be honest, was all algebra 1 stuff. How do we classify a polynomial? Well, we call it a monomial, binomial, trinomial. What's the degree, leading coefficient, leading term? How do we write it in standard form? And then the types of polynomials, we've dealt with all of these just as a mixture. And then what do these things do to our graph? Well, the leading coefficient tells us if it opens up or down. The degree tells us the end behavior. So there's a connection into all that. And we'll review that throughout today. And then we had quadratics review. This was all a review from Algebra 1 quadratics and Algebra 2, really. Can you find roots which are the same as solution, zeros, x-intercepts. All of those kind of roughly mean the same thing. So given a graph, can you identify those? Can you identify vertex, max, min, and others, extremas? Extrema is like a local max or a local min. End behavior, we'll review that again today, but can you look at what's happening at the far left or the far right of the graph? Leading coefficients are positive or negative. That tells us if it's increasing or decreasing. Axis of symmetry, and then algebraically finding roots. That's basically what we just did in the warm-up here. Use the quadratic formula. And then the y-intercept for any function, it doesn't matter where you're at. The y-intercept is always when x is equal to 0, plug in 0 and find the y value. So we did a big review. We basically spent a week reviewing, and then we got into some newer things. So section 2.1 was analyzing graphs, and this was basically from a graph, can you tell me all of this stuff? Right? Maxes and mins, these are locals or absolutes. End behavior was what happens as the limit as x goes to positive infinity of the function. Where is it going? And then we asked you to do it from the other direction. Can you look at the graph and from the far left of the graph, as I go to the far left, what's the function doing? Where's the output? So that's what we mean by end behavior. Right? And then find roots, increasing, decreasing. Is the function positive or negative? And then we spent a good amount of time analyzing polynomials algebraically. So could you do all this stuff algebraically? Well, factoring and quadratic formula and long divisions helps us find the zeros on the graph. Writing polynomials from a table, we're going to look at that here, but it's basically what we just did in the warm-up. And then long division is the skill that we need to do this material. So that's where long division came from. And then last week, I believe this was last Friday, maybe Thursday, I don't remember, asymptotes. To find vertical asymptotes, you factor the top and the bottom, check for holes. If a numerator and denominator reduces out, then that's a hole. We'll look at an example like that today. And then you set the denominator equal to 0, and remember asymptotes are always written as x equals for the vertical. All right, and then horizontal asymptotes, that ties into the end behavior asymptotes. That's where you compare the degree. So if the top degree is smaller than the bottom, that's an automatic 0, y equals 0. If the degrees are equal, then the leading coefficients is the horizontal asymptote. And if the top degree was bigger, then the slant asymptote is the long division. And we'll review that today. So this is on our Schoology page. Use it as a checklist. All right, I just want to show you what to expect because I felt like our first test, we had a lot of questions and students, I don't know if you read everything carefully. So that's what we're going to do right now is we're going to read this today so you have hopefully a full understanding. Here's our agenda for this week. All right, today we are reviewing for the test in class. Your homework tonight is a Chapter 2 study guide, but notice you do not have to complete every problem, which means this is optional. Okay, you need to do what you need to do. All right, if you feel like you got it, then you don't have to complete this. I'm not even going to have you turn this in. This is something you're going to do for your own benefit. But I do want you to know that the skills that we're going to use to create your test are from this study guide. So if you know the study guide, then you will basically done every problem that could be on the test. All right? The other thing to keep in mind is that this is going to be the remediation. So if you don't do well on the Chapter 2 test, then you'll have to go back through and do one problem successfully from that long list of each category. And if you do that, then you're guaranteed a 70%. So it's something to think about. If you study now, you're most likely going to do well and be prepared for the test, so you don't have to worry about doing a retake or a remediation. All right, there is no school on Wednesday. There's no new assignments. We're not going to meet or have anything on Schoology. But what you should do is continue studying for your test and work on any Chapter 2 homework. The due date for the Chapter 2 homework is Wednesday night at 11:59. Because on Thursday then, you're going to meet on Zoom, we're going to take attendance, and then you're going to do the Chapter 2 test in class, and you will be asked to submit your worked out solutions. All right, so I want you to understand that from the start. You're going to be asked to write down your work for every problem, and that is going to be part of the grade of the test. It might be 5 points, it might be a little more depending on the type of problem. And then you'll submit that work as a separate assignment that is not connected to the test. So basically, you're going to be given the class time to take the test, and then after that, you'll have the time that you need to submit. So this is what our slide is going to be, and I kind of already talked to it. So what do we got for tonight? Delta Math optional. You do what you need to do, but note that this will also be the remediation assignment. You need to accurately complete one problem from each category in order to receive the 70%. I'll tell you what, the students that did the optional review guide, actually the ones that did it before the test, they all scored like, and they did it well, they did scored like 85 to 100% on the last test, which tells you how nice this is. Okay, but it's optional. I'm not going to even have you turn it in, so you do what you need to do. All missing work is due by Wednesday, and then the Chapter 2 test is going to start at 9:30 on Thursday. So if you're late for class, then you're losing out on that time to take the test. So you need to be ready to go at the start of class and then have a piece of paper to write out everything. Okay? Right now, I want to open it up. Are there any questions on our Chapter 2 test for Thursday? Because I don't want to spend the first 15 minutes of class talking through that on Thursday. I want you to check in, and then we'll start. So you can unmute yourself and ask, or you can type it in the chat bar. I don't want to take the time in class to do this type of problem because you're going to see it's very similar to kind of what we did at the start. It's just a little bit of different directions. I'm just going to set this one up. So don't write this one down. I'd rather spend our time on other things. But let's just take a quick look. So what do we have? The function f is a quartic, which means it's degree 4. And it has the following tables, values in the table provided. Write the equation of the quartic polynomial in standard form. So what I hope you guys are connecting with is when we see this standard form in quartic, it's just the form, and I can't technically use k for everything. K is my generic piece, but I should have 4 zeros in this piece, and k can be a different value. So where are my zeros? Well, that's when your output is 0. So there are my 4 zeros, and then I'm going to rewrite those as this function. So what do I have? I have x. Now notice, this is the same as what we did in the warm-up. My solution is x equals -2. Well, if I plug this in, it's subtracting a negative, or think of this as moving over. So it's opposite of what the table reads. So I'd have an x plus 2 there. And then this one, if the answer is x equals 1, if I move the 1 over, its factor is x minus 1. It's basically the same thing we just did in the warm-up, but now I have 4 different answers. Okay, and the last one is x equals 3. So if I move the 3 over, and then the only thing that's left is the a value. So we put the zeros as factors. Step 3 is the one that you get to choose. The only thing you can't do is you can't pick one of the zeros. You have to pick a different point. It's usually recommended that you use the y-intercept because that makes it really quick and friendly. So if I plug in the y-intercept, that means every x is a 0. And then I just have to do some quick algebra. And if you multiply all this together, notice how you have an odd amount of negatives. So this would be negative, and 2 times 2 is 4. 4 times 3 is 12, so negative 12a. Divide by negative 12, and we get a equals 4. So I'm going to go back to the original spot where we saw a and plug it in. Now this is the part that I'm just going to kind of stop at. What you need to do next then is a whole bunch of multiplying. I would multiply these two together, and then I'd multiply these two together, so you're going to get a trinomial times a trinomial. And then you're going to multiply the two trinomials together, and that's where I would set up the big box and multiply those together. And that's the part I just don't want to spend that time right now today. I feel like you guys can do that, and there's problems like this in the review. So once you multiply all those together, you're going to get 4 terms, actually 5 terms because of the constant, and then you times it by 5 and you're done. So I don't think we need to really write that out, but we did a lot of those, so hopefully you're comfortable with it. These are the ones I want to focus on today. This is kind of designed to review what we did last Thursday, but also make sure we hit all the important pieces. So go ahead and write this down. Determine all the asymptotes of this function. Well, we have 3 different things to check. We got to check for vertical asymptotes. We've got to check for horizontal asymptotes. And if there aren't any horizontal asymptotes, then we have to check for that potential third option of the slant asymptote. So let's start off with vertical asymptotes. Now, from the instructions that we had last week, what do? We factor the top and factor the bottom if necessary. Well, the top here, the only thing we can do to factor the top is pull a 2 out. But that 2 doesn't really help me see that there isn't an x plus 3 up top. So that means we'll have no factors reduce out. So therefore, there are no holes in this graph. And then oh, by the way, let's say that this was a test question, and I'm going to ask you to show your work. I'm going to model what you should do when showing your work. And by the way, this should be neat. I shouldn't, like if it's on a piece of paper, I shouldn't just kind of do things randomly. I should really call this, let's say it was question 2 on the test. Okay, I should label it question 2, and then I should show my work in a nice order. So what do? We set the bottom equal to 0. And then quick solve. And there's my vertical asymptote. At x equals -3, there's going to be a dotted line vertically going up and down. You don't have to graph this, but I'm going to just do a very quick sketch so we can get an idea of what that looks like. All right, cool. We checked vertical asymptotes. Now we have to check the horizontal asymptotes. Horizontal asymptotes, you compare the degree. The degree is 1, and the degree here is 10, or x. X to the first power, x to the first power. So what do? When the degrees are the same, you compare the coefficients. I like to think of it like this. We're really just looking at the first beginning pieces, because if we were going to horizontally, if we're going to the far left or far right, that would be the limit as x goes to positive or negative infinity. Well, in the long run, if we get rid of this extra fluff at the end, the x's just go away, right? Those reduce out, and what's left over is 10 over 1. So then I've got a horizontal asymptote at the equation y equals 10. So what would my graph look like? Somewhere up here, we get the graph y equals 10. Now, notice, and don't waste your time here, this is a test-taking tip. Since the horizontal asymptote exists, you automatically know there is no slant asymptote. And the reason why is the degree on top is equal to the degree on bottom. So therefore, the horizontal asymptote exists. Okay, and let's do this. We're not going to do this for everyone, but they didn't ask me to. But since I'm kind of drawing a graph, maybe we can just kind of take a look. Where would my y-intercept be? Well, the y-intercept is wherever x is equal to 0. You're just going to plug 0 in. Plug 0 into the original function. What's left over? We get negative 14 over 3, which isn't pretty. But that's like negative 4 2/3, which would be, this isn't drawn perfectly, but it would be somewhere down here. And that's the only thing we can really tell from the graph is these items. Everything else, we would either have to create a table to graph, or we would just plug in, but our graph is going to look basically like this. So that's where we kind of estimate the rest of the graph. Now, since you're going to be taking a test on Desmos, you're not really going to have to graph by hand. But in my mind, if you can do all this, then you're making stronger connections to why we're doing what we're doing here. Okay, you know what? There is one other thing we can do. I was just looking at this, and notice right here, there's a solution. So let's just do this one last piece. Where do the x-intercepts occur? Well, the x-intercepts occur when the function is equal to 0. So when the y value is 0, and this is kind of an important thing to think of. Well, wait a minute. How do I solve a problem that looks like this? Think of it as a cross multiply. We can always put 0 divided by 1, and then if I cross multiply, I get the top part timesing by 1, and the bottom part ends up being 0. So really, what do? We just set the top equal to 0, and then solve. So bring the 14 over, divide by 10, and each one of those is divisible by 2. So here is the solution. 7/5, 0. That's my x-intercept. That's the only other thing we could actually find algebraically. All right, now our goal is to do this a couple more times And we're not always guaranteed to get vertical asymptotes or horizontal asymptotes, and sometimes there's a slant. I don't want to spend time, we're not going to do the y-intercepts, we're just going to look at asymptotes for the next couple problems. So I'd like you to try this. I want you to find just the asymptotes. Check vertical, horizontal, and possibly slant. And I'll give you, okay, this one's tricky. Let's take a look here quick. Very first thing you have to do is take the numerator and factor the numerator. So this is a perfect square, or a difference of squares. X plus 4x minus 4. On the bottom, I've got two terms. Now notice that it's not the same as a constant term here. So I have to just take away what's in common between both of them, and it's a 2x. When I take a 2x away from both items, I'm left with x plus 4. And then you're going to hopefully notice something. You get an x plus 4 reducing out. Now think about this. If x plus 4 reduces out, what is happening at the opposite of that, or what's happening at x equals negative 4? And that is our hole. So there's a hole in the graph when you have a common factor on top and on bottom, and it's not at 4, it's at what makes this equal to 0. So I solve. So there's a hole at x equals negative 4. And we'll show that when we look at the graph. So what does that mean? Well, that means we have to find the vertical asymptotes with whatever's left over. Well, what's left over? What's left over is the 2x in the denominator, and we're just going to solve. So we have a vertical asymptote at x equals 0. The next thing we're going to do is we're going to check the horizontal asymptote. Now notice my degrees are both x squared. So I like to think of this as just x squared over 2x squared. And this extra stuff, it's going to go away when we go to the really far left or right of the graph, because what's controlling it is the highest degrees. Now, we could tie this into calculus and put the limit as we go to the far left or far right. Well, all that's doing is saying is the x squareds are going to go away, and what's left over is the leading coefficients of 1 over 2, which means there's a horizontal asymptote at 1/2. And since the horizontal asymptote exists, the degrees are equal, there is no slant asymptote. Okay, so let's just do a quick check. You don't have to draw this, and I doctored this up a little bit. I want you to be aware of this. I originally plugged this into Desmos, and this is what my graph looked like. Okay, I typed in the original problem. Notice it doesn't show you the hole when x is equal to negative 4. So I just kind of had to use my Smart document and create a hole, because I want you to be aware that that's what it would look like. The only way you're going to find that is if you scroll over with your cursor and it pops up. So your calculator or Desmos is not going to identify holes. You have to be able to identify that. And then what does this look like? Well, at x equals 0, here you can see my vertical asymptote. And then at 1/2, see if I can do this right. At 1/2, there's my horizontal asymptote. You can see the behavior of the graph, and there is no slant asymptote then. All right. So yeah, really good question here. Ethan just asked, wouldn't it be at positive 4? Now notice, x plus 4 ended up reducing out as a factor, but when we graph, it's the what makes those 0. It's your solutions of those factors that tells us where the hole is. Because picture this, if x is equal to negative 4, and I plug -4 in right here, I get -4 plus 4, which is 0. And 0 is an undefined term when you divide by 0. So that's why the whole has to be at what makes this 0, not what the factor is. Okay. I'd like you to try this one. All right. Let's take a look here, and I'll kind of show you my approach for this. Since I know I'm going to have to factor the top and the bottom, let's take a look at that factoring here. The top part is just 2x minus 9, and 2 doesn't go into 9, so that's going to stay as is. But the bottom, there's two things you can do. First, I'm going to pull out a factor of 3 from each one. But then all of a sudden we get x squared minus 25, and that is the difference of squares. So we get x plus 5 and x minus 5. So here's the factored piece. Now notice, nothing reduces out, so there are no holes in this graph. But by doing that factoring work, now I can just take the entire denominator in its factored form, and we're going to set it equal to 0. Technically, I would divide by 3. If I divide both sides by 3, that gets rid of the 3. 3 reduces out, 0 divided by 3. And then I'm left with x plus 5, x minus 5 equals 0. So that's our zero product property. We're just going to set each one of those equal to 0 and solve. So I get x plus 5, x minus 5, and x plus 5 set equal to 0, and then just solve. So we get x equals -5 and x equals 5. I'll show you what that looks like on the graph, but there's my vertical asymptotes. So now our horizontal asymptotes, we're going to grab just the leading coefficients and leading degrees. So I like to think of this as just 2x over 3x squared, and forget about all the extra fluff, right? Because this stuff won't matter if I'm going to the far left or the far right. Well, what's going to happen then? I've got an x to the first over x squared. The degree on top is smaller than the degree on bottom. Well, technically, if I get rid of an x on top and on bottom, it looks like this. And what happens if I go to positive or negative infinity? Well, the bottom is going to get really big, which is basically going to turn into 0. So there's a little bit of a calculus connection that I'm trying to make, but the other thing is if you realize the degree on top is smaller than the degree on bottom, you're always going to get a y equals 0 horizontal asymptote, which means there are no slant asymptotes. Okay, so let's just take a look quickly at what this graph would look like. What do we know? We know that we've got a vertical asymptote at positive and -5. And then we've got the horizontal asymptote at x equals 0. And you can see the behavior of the graph models that perfectly. And there are no weird slant asymptotes. Okay, last problem. And you can probably guess what is going to occur because we haven't seen it yet. Determine all the asymptotes for this function. So I'll give you a minute to work on this. And then we're going to go over this one a little sooner than the other ones, mostly because I want to make sure we get through it all the way. So what do? We got to factor the top and the bottom. Well, the first thing is I can pull a factor of 2 away from the top. And notice when I factor the top, this gives me x squared minus 49, which is the difference of squares, x plus 7, x minus 7. So we did have to factor that, but you'll notice that it doesn't reduce out anything on the bottom. So the x minus 3 doesn't reduce out, which means there are no holes in this graph. And the vertical asymptote is very quick to find then. Set the denominator equal to 0. And we got a vertical asymptote at x equals 3. So then we're going to check for horizontal asymptotes. And that's where we're just going to compare if the degree on top is bigger than the degree on bottom, there are no horizontal asymptotes. Right? And that's our key. If there's no horizontal asymptotes, then we have to check the slant asymptote. And this is the one that requires a little bit of work. We need to do long division to figure out what is present or what's left over when I take x minus 3 and divide it in. Now, there's a little bit of a trick here. Notice how it goes 2x squared and there isn't a middle term. You need that spacer in there. That hasn't come up often. And I think Delta Math doesn't really do that too much. So you have to be very aware that if you're missing a term, you need to fill that spacer in. Otherwise, your like terms won't line up. So now it's just long division, and then we're basically done. I've got x. This x has to look like the 2x squared, so I'm going to multiply both pieces by 2x. Right? And then we add the opposite. So this becomes negative and this becomes positive. And then my x squareds reduce out. And I have 6x minus 96. And we finish this off by making this x look like the 6x. So I'll distribute that 6 each item. And then remember, add the opposite. So these become opposite signs, and then add it together. 6x's go away, and you're left with negative 80, which we don't really care about the remainder when we're looking at the slant asymptote. The slant asymptote is just the equation of what's left over. So if I was doing this as my work, I would indicate we have a slant asymptote at the equation 2x plus 6. Okay. So then what does that look like on the graph? Let's just kind of make sure everything makes sense. Now you'll notice right away I zoomed way out on this graph. If you were to graph this on your calculator, you would barely see just this first bump, and you would definitely miss the second branch of this. So, all right. So where do I have my vertical asymptote? This is at x equals 3. Now this is a very small or it's actually a pretty large scale, so it's going to be really hard to get that asymptote perfectly lined up, but that looks okay. And then where is the equation? Did I make a mistake? Did I miss a negative? Oh, you know what? I do know what happened. I was playing around with the negative. This graph actually should be inverted. So this is why it doesn't look like it. I was playing around with, I was wondering if I wanted to put a negative here, and I forgot to change the graph. So this is not the equation of 2x plus 6. This is negative 2x minus 6. This graph is the wrong graph for this function. It should be, this isn't great, but it should look like that. So that's my fault. I remember playing around with it, and then I decided against what I was originally going to do. But hopefully you can just kind of use this roughly and see there's my slant asymptote of 2x plus 6. All right, so long division is what gives us the slant asymptote equation, and it's just what the ends are doing, which is why the remainder doesn't come into play, because we're not looking at what's happening here. We're looking at the far end behavior, which, by the way, this graph might be a really nice one for us to talk about. If I was looking at this graph, what is the end behavior? Well, as x goes to positive infinity, where's my graph going? As I go to the far, far right, this graph is going up, but up isn't our official term. We're going to positive infinity. And then the other direction, what would it be as x goes to negative infinity? Well, as we go to the far, far left, you can see your graph is going down, and that's equal to negative infinity. So be used to writing the end behavior as well. Okay. I already went through this, so your homework tonight is to just go through the chapter review and do what you need to do. Okay? If you get it 100% done, then you basically can already guarantee yourself a 70% on the test. Work on any missing work. That's due by October 28th at 11:59. And then the Chapter 2 test is on Thursday. You need a scratch sheet of paper, and you're given the time in class. So if you have any questions, please let me know. That's all I got. So you guys can head out a couple minutes early.